Darwin is celebrated as the founder of ecological thinking because he showed great sensitivity to the subtle patterns of checks and balances. But climate change, as we've heard, not only this morning but also during the week, differs from any other problem that humankind has ever had to face, because if it goes unchecked, the consequences are likely to be catastrophic. And Professor Sir Brian Hoskins is a dynamical meteorologist, the Royal Society Research Professor at the University of Reading, Director of the Grantham Institute of Climate Change at Imperial College London, and a member of the UK Committee on Climate Change. He was one of the Nobel Prize-winning team on international climate change assessment. When he was asked whether he can accurately predict the weather, Brian jokes by saying he's always very wise after the event. Please join me in welcoming Brian Hoskins, who's going to speak to us about the future for the environment on planet Earth.
It's a great pleasure to speak to you today about this, and I gave a rather genteel title to the organizers here, but I prefer the other ones, What Are We Doing to Planet Earth? Now, I'm going to discuss a number of global environmental problems. The concentration will be on the second one, global warming, but also I will be mentioning all the other problems because they have interest in terms of, they're all provoked by our population and by the waste matter that we're producing in terms of our standard of living and the way we wish to live. So what we do with that in terms of the air, the water, and in terms of the habitat around us. So I will start with the ozone hole because there is a note of optimism in that, and as before, I will try and inject the optimism where I can, but it's not a bundle of laughs, I assure you. So let me start with the ozone hole. The black line here is the record obtained by the British Antarctic Survey scientists, Joe Farman in particular earlier on, where they measure the column ozone. So that's looking at all the ozone above them, and that ozone protects us from ultraviolet radiation. And what they were seeing each spring in Antarctica, and they were looking at this in 1980, and they saw, is this curve going down? And this is always a difficulty for scientists. Are we looking at natural variability and it will come straight back up, or are we looking at a trend? And in 1980, the warning signs were there that in the Antarctic spring, the amount of ozone was going down year by year. And in 1985, they actually, after urging from many people, published their paper to discuss or mention and bring to the world's attention the ozone hole. And at the same time, then big scientific campaigns were launched in order to find out what was going on. And then, having discovered what was going on, the Montreal Protocol, an agreement between the nations to do something about it in 1987, and this was followed by various others in Copenhagen, London, and Beijing. And the situation isn't good, but at least it's bottomed out. It reminds me a little bit of the recession, about whether we're bumping along the bottom and whether we're going to go back up. But that's where we are at present. And if one looks at this, then these are pictures from space, and the left-hand one shows what the situation was in the Antarctic spring before the ozone hole really started, and then the right-hand one shows what it's like with the ozone hole. But there's a cautionary tale here because NASA did not find the ozone hole. They had ruled such low measurements out when they analyzed the data. So it was only the in situ measurements that actually showed this was going on. And so there's a lesson there about in situ measurements, and the second lesson is about not ruling out the unexpected. So this is what was going on in terms of the vertical distribution. You see in the blue curve there what the ozone should look like and what it looks like before the springtime loss. And the ozone there peaks around 18 kilometers. And then you can see in the red curve the great bite taken out of it when the ozone hole develops. And the explanation was found in terms of CFCs, sunlight, and these polar stratospheric clouds where the atmosphere is extremely cold, as shown by the green curve. The CFCs, and we were using CFCs for propellants and refrigerants because CFCs were so stable. They wouldn't cause any problem, they're so stable. And that, of course, meant that they would be distributed throughout the atmosphere, in particular to the upper atmosphere, where, in terms of these special interactions involving the clouds and when the sunlight switches on, the chlorine was released and attacked the ozone. So that was what went down, and that's what the science understood, and then the nations acted in terms of the Montreal Protocol. Now, in terms of the recovery, because my brief was also to look forward, so you see in the red dashed curve projections of when the ozone hole would return to almost normal and maybe rebound beyond. And that was going to be somewhere around 2060. But you also see a red curve here that with climate change is actually thought the recovery may happen about 10 years earlier. So that moves me on to then climate change and global warming. And I thought I would do my sort of basic thing in what is all the fuss about, because sometimes I think people think this is ideas that have been generated in the last few years and they're all very flimsy, but it really is, the basic theory has been there since the early 19th century. So there we have the blue dot, the blue planet, and the driver of the weather and climate is the sun's energy streaming down the yellow arrows there, and the balance of energy then is in terms of the heat given off by the Earth in all directions, the red arrows. Now, the crucial thing then, the greenhouse gases, they are transparent to the solar radiation. They allow it through, and so the radiation can come down to the surface of the Earth if it's not intercepted by clouds, etc. However, the thermal radiation, the heat given off by the Earth, is actually absorbed by these greenhouse gases and eventually escapes to space from about 5-kilometer level of the atmosphere, where it is colder than at the surface. So the amount of energy radiated to space is much less than if it was radiated from the surface. So these gases then allow the planet, the lower planet, to be much warmer. And if we add more greenhouse gases, then the level at which those emission to space would occur would be higher. That's where it's colder, so less heat would be lost, and the planet would warm up until a new balance was achieved. And that's what we're talking about with greenhouse gases and global warming. And these ideas have been around since a certain gentleman, Fourier, 1827, who hypothesized that this effect must be there. And Tyndall, at the same time as the Origin of the Species was being published, Tyndall was in his laboratory actually looking at the absorption of infrared radiation, of this thermal radiation, by water vapor and carbon dioxide. And water vapor is the #1 greenhouse gas. Now, you don't usually hear people saying we must reduce our emissions of water vapor in our activity, and that's because water vapor is such an inherent part of the climate system, continually being recycled and dominated by that. What we can do can only influence very, very locally. However, carbon dioxide, methane, nitrous oxide, a different story. Oh, grief. Okay, the time lapse here is... Right, thank you. Right, so what happened to the carbon dioxide? How have we released this carbon dioxide to the atmosphere, and what's happened to it? And you see above the axis, above the zero line then, the sources. And in the early time, the brown color there, this was due to deforestation mainly in our middle latitudes. Whereas that turns then to the lighter brown curve, which is now the deforestation in the tropical regions. But dominating those then is the release due to our burning of fossil fuels. And that's the gray area above the axis. Now, what's happened to all that CO2? We are extremely lucky that only about 45% of that has finished in the atmosphere. The ocean has absorbed a considerable amount, and so has the land surface. So the ocean and the land between them, the terrestrial biosphere, have managed to sequester that carbon and leave us just 45%. The amount actually more recently has been only 40%. There's evidence that the ocean is no longer absorbing quite as much CO2 as it was, probably because of the increase in surface winds in the Southern Ocean linking to the ozone hole and climate change. So there's a sort of feedback in the system there. The land has been absorbing rather more as the carbon dioxide has fertilized the biology on the land surface. But that's the situation, that's what's been happening. And this is the actual measurement of carbon dioxide in the atmosphere. Carbon dioxide becomes well mixed, so it doesn't really matter too much where on the Earth's surface you observe it. And these are the measurements been taking place in Hawaii since 1957. And the raw data then is the red curve. And the first thing you see is the annual oscillation, which is, if you like, the Earth breathing. This is because the majority of the vegetation is in the northern hemisphere. So when it's growing, it sucks up the carbon dioxide, and in the winter then it releases. And one sees the bias of the vegetation in the two hemispheres. But beyond that, you see then the black curve, the trend upwards, increasing about 2 parts per million per year. So in 1 year, we're putting back into the atmosphere what it took the Earth system about 1 million years to put into the Earth. So this is the imbalance in the energy budget at this current time, as given by the Intergovernmental Panel on Climate Change. And I have a few slides from the 2007 report. And you can see the dominant one at the top is carbon dioxide. But also the methane, nitrous oxide, halocarbons are present there. It's an interesting effect that actually, as someone said the other day, the CFCs, because they cause the ozone hole, we were very lucky, because if we had kept using them, they would have had a huge impact on global warming. So we were lucky that they were ruled out for other reasons. However, substitutes are also bad in this game as well. And you see stratospheric ozone playing a role, tropospheric ozone, which we'll come to later on, being a significant warming too, but that's also in air quality. Then the albedo, the reflectance of the land surface. But then big terms on the negative side associated with what are called aerosols, little particles in the air. So some of the filth we're putting into the atmosphere, obscuring the sun. However, the error bars there are large, you might notice. And the total is almost the same as the CO2 itself, but with a lot of pluses and minuses. Now, I've only got one picture here. It was very difficult to know which one to put in. But this one shows on each of the inhabited continents. The black line shows the temperature curve over the last, since 1900, so the last 100 years. And we can see in each of the continents the temperature has risen during that period. And then the models have been run to try and simulate this last period. And the blue range of models is when the increase in greenhouse gases is not put into those models. And on no continent does the observed record lie within that blue set of curves. But if we put the increase in greenhouse gases into the models, then on every continent, the increase in temperature is within the range of the models. It's a very good evaluation of the models and an attribution of the observed temperature rise to the greenhouse gases. Now, I'm just going to put in one slide in terms of what's happened since the IPCC report. This is the Arctic sea ice situation. And every September, there is a minimum in the Arctic sea ice. And one can see that when we wrote the 2007 report, we had the data up to 2006, and there was a downward trend. And we wrote the report, and along came September 2007 with a value way below any of the models at that time. 2008 was just a little above that, and we wait with bated breath to see what 2009 gives us. And you can see the numbers here are very significant. We're seeing almost in that period a halving of the sea ice in that September minimum. In 2009, we do have some measurements already. In March, when the sea ice was at its maximum, one can look at the age of the sea ice. And on the left-hand side, you see what is the normal age of sea ice. Most of it at least 2 or more years old. This year, most of it is only 1 year old and probably thinner. So this leaves it as particularly vulnerable then to what's going to happen this summer. One picture for then a projection of what the temperature and precipitation might be in December to February in the 2090s if we continue on the present course. And the global average is around a 3-degree rise from about now at this time. But we don't live in a globally averaged world. And if you look locally here, you see over the northern continents in particular, a lot larger temperature rise than that global average. And on the high northern continents, you're looking at something like 2.5 to 3 times. Maybe the permafrost region 8 degrees warmer. You can imagine the permafrost is not going to enjoy that, and neither would we. But perhaps almost more worrying is the precipitation. The speckles here, I should say, where 90% of the models agree. And precipitation is more difficult. I think the main thing you could say is precipitation will change. And in particular, the dry regions will tend to be drier and the wet regions wetter. And here we see the northern continents in their warm winter being much wetter. But then places like the Mediterranean not getting their winter rainfall and the southwestern US. And the impact of these changes in rainfall could be very severe indeed. One, to show the commitment. We're already committed now to the climate change that is going to occur over the next 20 years. So 2030 we're already committed to. But this actually shows a commitment way beyond. These are some calculations that, again, that were in the IPCC, but a paper recently has highlighted this, that if we let the CO2 levels in the atmosphere rise to certain levels and then emit no more CO2 to the atmosphere after that, we see the CO2 levels do not just go down to zero, back to pre-industrial levels. After 1,000 years, you've still got at least 40% above the pre-industrial level. And if you look at the temperature on the top right, then having reached that maximum temperature, on no case does it drop by as much as half a degree within 1,000 years. And the sea level, the thermal expansion of the ocean, goes on for 1,000 years and more. So we are committing for thousands of years our planet in terms of what we do now. One problem that's become much more apparent in recent years is that as the CO2 level rises in the atmosphere, then the ocean is becoming more acidic. This has already been measured and is expected to continue in the future. And this is going to put a stress on little animals in the ocean with their shells and corals, etc. So yet another manifestation of the increase in greenhouse gases, and one that would not be cured by just fiddling around with the temperature. Now, the Climate Change Committee that I serve on, and so does Bob May, we produced a report last December in which we were to produce targets for the UK. But to do this, we had to look at the world situation first. And on the left-hand side, you see some scenarios of emissions that we came up with for the world. And the blue line is the sort of business as usual, except there's no such thing as business as usual. But that's the curve we're on. And the lowest curve there is about the one that we thought should be handled. And if you, in terms of today's models, if you look at the impact of those emissions, then we get the picture for temperature, globally average temperature on the right-hand side, where the median, it's a probability distribution. It is uncertain due to our lack of knowledge and due to the climate system itself. However, the 50-50 point, as our present understanding, is about a 2 degrees, slightly over 2 degrees warming. There's nothing magical about 2 degrees, that 1.9 is safe and 2.1 is sheer hell. But the less we can keep it, the better. So keep it near 2 degrees. But we had another criterion as well, that we wanted the chance of going to that 3 or 4 degree world to be down at the percentile level, because that's a world we dare not enter. So if you look at that, we're talking about world emissions peaking by 2020 and descending at about 3 or 4% after that. And has already been mentioned, this means that every citizen in the world, if one divides it by the 9 billion, then is entitled to 2 tons of CO2, or if we're thinking of the equivalent of all those methane and everything else, it's slightly more than that, but we should include all the greenhouse gases. Now, in the Climate Change Committee, we said we cannot envisage a situation in which the UK or any other developed country could have a greater allocation than that in 2050, and that means an 80% cut for the UK. And that is now in UK law, that target. And 2 days ago, then, the G8 came out with very much a similar statement, although they were rather hazy on when the 80% cut was compared with. But importantly, as urged by various developing countries, we also, for the UK, have targets for the next 15 years as well. For instance, 2020, we're talking about a 30 to 40% cut in our CO2 emissions. So we're now on the road to Copenhagen, so question marks. I'm now moving to a few other problems that I want to mention, and they are separate problems, but they tend to be related as well. But I wanted to give a rather more complete view of what we're doing to planet Earth. And poor air quality, near-surface ozone. So we've talked about ozone in the stratosphere. Ozone in the stratosphere is good. Ozone down here is bad. And we've seen that the ozone down here contributes to the greenhouse gas global warming problem, but it also affects health in a very bad way as well. And these are some calculations for what the future ozone levels might be. There's associated with the anticipated emissions of the precursors of ozone and also of the climate change, because ozone, the production of ozone is very much influenced by the ambient weather. And on the left-hand side, you can see the projected ozone levels for the 2090s. And it depends who you talk to, what is a safe level. Probably there is no safe level of ozone. But these levels being shown here of 60 to 80 in a widespread region and above that are really damaging to human health. And on the right-hand side, you can also see they're very damaging to plant productivity as well, where you're seeing projected reductions of 20 to 30% associated with those ozone levels. Just a little comment, Africa seems to figure badly on almost anything you look at here, and yet again, Africa, they're figuring in terms of the reduction in productivity due to the enhanced ozone levels. The particles in the atmosphere I've already mentioned as coming into the greenhouse gas global warming problem, in fact providing a negative there. But again, in terms of human health, then rather serious implications. Here we see a picture actually of what is often called the brown cloud coming out from Asia. And you can see it streaming out over the Indian Ocean there. And it's a debating point or a scientific discussion at the moment, what that is in terms of what impact that has, for instance, on the Asian monsoon. But there's no doubt it has impacts in terms of the solar energy received at the Earth's surface. And if you see in the top curve then, what is the change, thought to be the change in direct solar energy at the surface from 1950 to 1980. It's an interesting thing, actually, in terms of the forests on Earth. This may actually have helped the productivity and the carbon actually absorbed into the tropical forests, because the diffuse radiation, the direct beam has been reduced, but the diffuse radiation has been increased. The sky looks white. And that diffuse radiation has been able to make its way through the forest canopy. And we may temporarily have had slightly more carbon actually taken up by the forest because of that. And of course, these aerosols have helped mask the greenhouse gas warming. Now, has that done us a good turn or not? Because in some ways, it's made us not have to be so aware of the problem. But there's no one who thinks that the aerosols are going to increase at the same rate as the greenhouse gases. And here we see, actually, for 1980 to 2000, over Europe, the aerosols have gone down. And it's only in limited regions of the world that the aerosols have gone up. And it is expected that that decrease in aerosols, or much slower increase, will continue. Now, this is not the world's most elegant slide, but I wanted to put in a couple of slides now to talk about some of the basic elements we have and what we've done to their cycles. So this is the global cycle for sulfur here. And you don't need to take in every number that's on this diagram, but you can see that both the land surface, the ocean, volcanoes, and rivers, they're all involved in the sulfur cycle. But along comes mankind, and you can see in yellow the new numbers, the numbers that are with our activity. So, for instance, the transfer from the land region in the atmosphere to the ocean has gone from 10 to 61. These are teratons, I think, of carbon, as far as I remember, and of sulfur. And if you look at the deposition on the land surface, leading to the acid rain, leading to increase in acidity, or just dry deposition, but acidity of the waters and interfering with the vegetation. So again, that's gone up from 32 to 84. So huge impacts on the sulfur cycle. Moving to nitrogen, then, you can see again in the little curves, the top on the left, that we've overtaken the natural fixation of nitrogen in terms of our activities. And we did that around 1980 and continue to rise. And if one looks at a particular part of the activity, then the nitrogen from fertilizers being washed into the rivers and then producing eutrophication in the rivers, oversupply of nutrients, and then those waters being washed down to the shore and the dead region being created with an oxygen deficiency. And from space, one can see this dead region near the shore. But then these are projections for the deposition of reactive nitrogen 2030 compared with 2000. And these projections, so in red, you're seeing numbers which are generally 10 to 50% above. So again, the projections suggest that in future, the deposition of nitrogen on the land surface and on the ocean will be increasing, again with its influence on the biosphere. Habitat loss. There's been a Millennium Ecosystem Assessment produced a couple of years ago, and they looked at the habitats, the various habitats from the Mediterranean forest down to the tropical moist forest there, and they estimated the loss that there's been in the period up to 1990. And you can see in some far more than half removed, in others still 70% remaining. And then they moved on to project into the future and said in terms of various scenarios, what might it look like in 2050? So in our region then, we're busy trying to put a few forests back, and perhaps that's the one that might go a little way back, but only a small way. But in the rest of them, the projections looked like a world where these habitats were continuing to be eroded through to 2050. And the picture I show you here then is again from the Millennium Ecosystem Assessment, looking at the drivers of change in biodiversity and ecosystems. So on the left-hand side, you see the various habitats, and then the drivers on the top there in terms of habitat change, climate change, invasive species, overexploitation, and pollution. And we've looked at many of these as we've gone through the talk here. Now, the intensity of the colors shows you the impact now on biodiversity and ecosystems, and the arrows show you the direction for the future as estimated by the Millennium Ecosystem Assessment. And you can see for climate change, for instance, the colors are intense in a few places, but the arrows are all up. And in terms of habitat change, intense colors now and some arrows up. Invasive species, similar story, and overexploitation, and the pollution that we've looked at as well. We've looked at the nitrogen and sulfur cycles. So the story is not a good one, and it looks one of continued stress on biodiversity and ecosystems. Now, I told you it was going to be a bit depressing, but I'm trying not to be depressed, and I will now try and wrap it up with a sort of optimistic look. We've looked at all these problems, and it's clear that with our population and with the way we've been living life, then this is leading to stress on the system. And the outlook for planet Earth and our existence on it is not good if we continue to behave in this manner. But we've already seen there are solutions. The ozone hole is one, for instance, where we observed, if you like, we listened to the planet. What's the message that's being given to us? We tried to understand that message, and we looked at what was the way forward, different ways forward, different scenarios, and how this could be tackled. In terms of the ozone hole, actually, it was the Montreal Protocol went through so quickly because companies in the USA and UK saw the opportunity to make money out of the alternatives from CFCs. So there's a lesson there. I think if the alternatives look like an attractive business proposition, then this is one way forward. So we have to understand, and we have to act together. We've seen this was managed in terms of the Montreal Protocol, in terms of the global warming, which is the overwhelming problem to me underlying much of this. We understand much of the problem we've observed. We understand much of the problem, and we know that there are solutions to limit the global warming. So the technology exists now, and the developments can be done over the next 10, 20 years. And the challenge is then, this is a unique challenge, because what we do now over the next 10, 20 years is going to affect the end of the century, and as we have seen, through to the next millennium. Can we act now for generations in the future in other countries? Thank you.
Thank you very much, Brian. Though I wonder whether we should thank you. It's been a somber story, and we probably need more than coffee. But let's break, and I suggest we come back at 11:15. Thank you very much.